Concepts. So the first key concept that we have here is we have a definition with a picture with an example. Okay, so we're first going to define it. It's kind of going to be a box like this. Okay, you're going to have a picture in the middle, definition on the left. So two polygons are similar if corresponding angles are congruent. So two polygons are similar if corresponding angles I'm going to use my symbol for angles. If corresponding angles are congruent, I'm going to use my symbol for congruent. And if the lengths of corresponding sides here we go, zoom in for you. If the lengths of corresponding sides are proportional. Okay, so there's our definition. And then we have a diagram we can draw. Of two trapezoids, one smaller than the other. So we have trapezoid ABCD. And we have trapezoid GHIJ. Now, I think sometimes the trickiest part about this is the naming. So we're going to say here ABCD. We've just named that first polygon. So ABCD is similar to GHIJ. Now the crazy part is I couldn't have said polygon ABCD is similar to polygon JIHG. That would mean something different. So the naming is key, and here's what I mean by that. When you look at angle A and angle G, so angle A and angle G, those are similar. Or sorry, those are congruent. The corresponding angles are congruent, right? And then if I look at angle B and angle H, you see how those are in corresponding positions? If I look at angle C and angle I, those are congruent. And then lastly, angle D and angle J. We need to do two there. So to be honest, I could actually determine which angles are congruent without the picture. All right, so now I'm going to write it out, what I just said. I'm going to write that in symbols. So in symbols, what we just said is angle A is congruent to angle G. Angle B is congruent to angle H. Angle C is congruent to angle I. Angle D is congruent to angle J. So there's that first part, talking about the angles, the corresponding angles are congruent. In this setup, we have the polygons placed strategically to be in the same position. If I rotated this polygon, this trapezoid around to a different position, then it becomes even more necessary that you match up the appropriate angles based on the way that they're named in the similarity statement. Okay? So then we're going to actually write what's called an extended proportion. So this accomplishes that second part of the definition. The lengths of the corresponding sides have to be proportional. So side AB over, so side AB right here over side GH has to be equal to side BC over HI which needs to be equal to CD over IJ needs to be equal to AD over GJ. So that's our basic definition of similar polygons in words, in pictures, and in symbols. There's a couple other definitions that we need to write down. Rather than writing it down in lots of words, let's just label that this thing right here, what did I call that? An extended proportion. Okay, so this is an extended proportion. I think by looking at it, you can understand that an extended proportion has 3 or more ratios involved in the equation, unlike a traditional proportion, which only has 2. The next definition we do need to write down is scale factor. You may have heard that term before. So the scale factor is the ratio of the corresponding linear measurements. So it's the ratio of the corresponding linear measurements of 2 similar figures. Okay, so for example, we're just going to draw a triangle, our simplest polygon. We're going to draw 2 triangles. I meant not just 1, but 2 triangles. ABC and a little one, X, Y, Z. I'm going to mark a few angles, just two actually. Well, if I know that these two are congruent and I know that these two are congruent, what has to be true of that third pair, they have to be congruent. They all add up to 180. So given this situation, we're going to label the side lengths 15, 20, and 25 for the triangle ABC, 6, 8, and 10 for triangle XYZ. So we need a similarity statement. Triangle ABC is similar to triangle XYZ. And now we need to, we can figure out our scale factor since we know, it's key that we know the two triangles are similar, and now we can write a statement to calculate the scale factor by choosing any of our side lengths and making a ratio. So we can choose 15 over 6. So let's do side AB over XY is going to be equal to 15 over 6. We can reduce that. What is the common factor between 15 and 6? 3. So we could divide both of those by 3, and we would get 5 over 2. Right? So the scale factor for these two triangles is 5 to 2. Other ways we could write that as 5 to 2 with a colon. We could write that as, using the words, 5 to 2. Why would it not be 2 to 5 or 2 over 5?
Because you'd be saying that the smaller triangle is bigger than the bigger one.
Right, exactly. It has to do with how this similarity statement is written. You know that the big triangle is first in the statement. So the bigger number, that's where we have to start in our ratio for the scale factor. If it were flip-flopped, it doesn't matter how the drawings are written or drawn, we would need, if it said triangle XYZ is similar to triangle ABC, it's assumed that the scale factor would then be written as 2 to 5. Okay, so this is key in many ways. All right, makes sense? Great.